All right, in this video, what we're going to look at is finding absolute extreme values of a function. And what absolute extrema usually requires is some kind of closed interval. And as you'll notice in the graph that I have here, we have some function f of x, which is this parabola-looking curve right here. It might be a parabola, might not be. And we're only focused on the portion of the graph between x equals a and x equals b. So we're looking at that segment of the curve. And you notice a couple interesting things there, and these are the kinds of things we need to check. Naturally, a maximum or a minimum value could occur at one of the endpoints. That's one of the beauties of having a closed interval, is that we can check the endpoints. So we're going to check endpoints. But based on what we know already is that a minimum or a maximum could occur when there is either a horizontal tangent line or when the derivative is undefined, what we call the critical numbers. So we also have to check the critical numbers. And what we do with this is, once we know the endpoints and the critical numbers, we substitute into f of x and compare. Which means what we do is we substitute into f of x, and the largest value of f of x is the max, and the smallest value of f of x is the minimum. So it is quite intuitive. So what we're going to do is look at a function. Let's look at f of x equals x plus 4 over x squared. And let's say we're on the interval 1 to 4. Now, what we might want to do is get a look at what the graph looks like. I can just provide that for you right here without going to Desmos. But when x is 1, y looks like it's 5, so we're up here somewhere. And when x is 4, it looks like y is, that's 4 plus 4 over 16, so just over 4. So we're kind of talking about this. And what I can tell you the graph does is it goes something like this. Okay, so we're only concerned with the piece of the graph that is between x equals 1 and x equals 4. So I had to backpedal on that there for a moment. So it looks like the highest value is going to be at 1, but just in case my graphing skills are not up to par, we're going to use calculus and actually plug numbers in here. So what we do is we find critical numbers, because that is where max and mins could occur that aren't apparent to us in the endpoints. So we'll first rewrite the function so that it's what I call derivative ready. In other words, I want to use the product of the power rule if I can. So we get 4 over x squared as 4x to the negative 2. And then the derivative is, the derivative of x is 1. And the derivative of 4x to the negative 2 is 8x to the negative 3. If we bring the negative 2 down, of course, that changes that to a negative, and we want that to be equal to 0. Okay, so now we use algebra to figure this out. Well, I'm going to add this to the other side. And remember that x to the negative 3 really means 1 over x to the third, so I'm going to rewrite this as 1 equals 8 over x to the third. And then I'm going to multiply both sides by x to the third. And if you want to know what number cubed gives you 8, well, that's just 2. So that means that 2 is my critical number. So then at this point, what we'll do is I'll make a little chart of x with its f of x and all the potential values where a critical number or where a min and max could occur. We could have something happen at one of the endpoints, and we could have something happen at the critical number. So again, when x is 1, I know we already did that before. That was 5. When x is 4, I know we already got 4.25, so no math is going to change that. When x is 2, we have 2 plus 4 over 2 squared. Well, that will say 4 over 4, which is 1, plus 2 is 3. So it looks like we have a minimum at 2, 3, and a maximum at 1, 5. And that is how we analytically determine the maximum and minimum values of a function on a closed interval. So I hope this helps get you started, and I thank you for watching.